So this is the last, course lecture. So it will be of a very different style than the others. So the others were, constructing, step by step, more or less in the case of percolation mostly. First of all, how you go from a discrete model to the continuous model, how you define the continuous model, how you study the continuous model, how you compute with it, and how you go back to the discrete model and prove things about it. And you saw that there were, many, many steps. And of course, one of the nice aspects of this entire theory, of this, story, or this journey that we did was that, it mixes many different type of arguments. There was pure discrete combinatorial type probability with, flipping and, the particle system type things with FKG and so on. And then there was, when we hit the continuous story, then there was conformal invariance, stochastic analysis, invariance, complex analysis, and harmonic analysis a little bit, playing with some energies and this type of things, even though we don't say it so loudly. And then stochastic analysis also, which is behind the scenes also, because once you hit the continuum, you are playing with Brownian motions and these type of things. And in a way, let me say something very vague, but if you think sort of, in the percolation picture, I said several times that the entire story, was to organize this two-dimensional randomness. You have randomness that is spread in some way in a two-dimensional lattice or in the domain. And, depending where you are, you have something random that happens, and they may interact or not. For instance, if you look at the Ising model, clearly they will interact. But, it's sort of spread sort of in the lattice or in the plane. As Christophe has shown you in his seminar, the way, these information that is located at different points, comes together and creates a macroscopic observable is very complicated because, they have the way to look at it in terms of Fourier spectra and things like that, but basically it's not like, you just integrate smoothly the noise that you have all over the place in order to see a macroscopic noise. So it's not what is called a white noise. Percolation is something which is much more complicated. Nevertheless, so when you try to understand these things, the idea is still, to try to explore this thing, progressively, like we do in percolation by unraveling, the colors of the different cells one after the other and trying to explore this mess in some algorithmic way. So it's always, you have a big mess and you try to order, this information in a one-dimensional way, right? Because when you flip, these exploration processes, the idea is to flip them one after the other and to have to sort of encode everything into a one-dimensional, story where the notion of time is clearly there. And once you are there, once you encode things in a one-dimensional way, then you are in safe haven because, probability theory and theory of martingale, theory of Markov processes and so on is precisely about, encoding, having information that, appears continuously in a one-dimensional setting and in a one-dimensional ordered way. So that's the general philosophy of this, right? That you have a big mess, and you try to, discover this mess in a one-dimensional way with respect to time. And so, of course, this is very special. It doesn't happen each time, for each model where you have a global mess, that you will be able to find a natural way to discover it in a one-dimensional way. So if you think of a three-dimensional problem, three-dimensional percolation or three-dimensional easing, or I don't know, then you may ask, okay, is there a natural way, natural algorithmic way to discover say, the cluster from the origin, you know, in some intrinsic, well-defined way, and you clearly see that, no, I mean, you know, you don't have this equivalent of these interfaces that you can travel along in 2 dimensions in a unique way. If you're on a 3-dimensional object, you know, you can go in all directions, and you have all sorts of topological problems appearing. You know, what is an interface is actually already a problem, you know, because, you know, an interface might be a surface, but then maybe you have, you know, little filaments, you know, that go from one surface to another, and then, so it's not clear what the interfaces actually are. Okay, I mean, so or you might define a good notion of interface, but maybe it's not the correct one to look at. So in 2-dimensional things are, you know, the notion of interface is something which is clearly given for you by the 2-dimensionality. So a similar, you know, problem was with, you know, if you're off-critical, you know, there were these results by Dobrushin and Kotevsky-Schlossman about, you know, large deviations of the shapes of droplets, you know, in Ising models or things like that. And so in 2 dimensions, they did this, or Pfister also, they did this in 2-dimensional, because then, you know, in 2 dimensions, you know, the notion of interface is something which is clearer, and then, you know, it was a problem to try to say, is there a 3-dimensional analog, right? And one of the key steps, you know, to proving and understanding things, in that case, from the 3-dimensional analog, was to find, you know, the right norm and the right notion of what interface is in 3 dimensions to have large deviations times results. So these are the result papers by Raphael Cerf, you know, where he shows that you have to take an L1 norm on these things. So, and these norms are clearly not, you know, things where you can see naturally an interface showing up, you know, that you can explore in a natural way. So everything here is really restricted to 2 dimensions. So maybe I will start with a few general statements about SLE itself, you know, about what are the results that have been just proved, and what is the global situation about the open questions about SLE itself as a process. And then I will try to move on and show you different things where people are have been making progress recently, and how to try to understand the things. And again, what is apparent is that it's nice because several different areas, you know, still, you know, can be plugged onto this this SLE story. So maybe the first thing I want to say is that if you forget about the lattice models, you know, you forget everything about Ising, pots, whatever. So you just look at SLE being defined as, you know, these random curves that are defined by putting a Brownian motion running at a certain speed in the Loewner equation, and this defines a curve, and what can you say? So what is proved, what is known, so for SLE is basically now that, you know, if you define FWT to be Brownian motion running at speed kappa t, then you solve the ODE given by SLE. So you solve this guy. You define define KT to be the set of Z in H bar such that the infimum over, how you say, WS minus GS of Z when S is smaller than T is equal to 0, something like that. So basically the points that have hit, that have been swallowed by this growing family, that's KT. Then what is known is that almost surely KT is generated by a curve. That means that there exists gamma, continuous curve gamma t, such that kt is the hull of gamma up to time t, which means that it's basically gamma up to time t plus maybe the loops that it has included. Right? And in particular, gamma t is nothing else than gt minus 1 of wt. So that basically, indeed, you know, when you have this thing and the place where things are growing is just the pre-image under gt of wt. So here I use basically this quotation marks because this means that gt extends continuously to the gt minus 1 extend continuously to the boundary of the upper half plane, which is not necessarily true, you know. So that basically the image of this guy is going to be actually a point here. You know, it might be something like these weird pictures Christophe has shown you. So this says that for almost surely for all t's, basically gt will extend continuously to gt minus 1 will extend to wt, and so you can recover gamma. So this says that for any, you know, that you can look at SLE with forgetting about all the all the discrete models, and you can look at it directly. So this statement, you know, it's not an easy theorem. Right? So I guess this result, except in the case kappa equals 8, was derived in a paper by Steffen Rode and Oded Schramm, that appeared a couple of years ago in the Annals of Math. And it's not, you know, it's not a trivial thing, because as I told you before, when W is a Brownian motion, it has, you know, it's not held at 1/2, so you cannot apply, you know, standard, you know, machinery to just check that you are not in trouble. So, okay. So you can look at SLE directly like this, and as Christophe has explained to you, it's not very difficult to see that basically, if kappa is smaller than 4, gamma is actually a simple curve. That when kappa is between 8 and 4, it is not a simple curve, so it's a curve that grows like this. And because of self-similarity, of course, you know that the set of times where it bounces on itself is almost surely, I mean, it's dense, you know, on the curve, because at each scale you will do this little bumping on yourself, and they will correspond to fractal type subsets of the curve. So, and when kappa is larger than 8, you have these strange guys that gamma is actually sort of a plane filling curve. So it's plane filling not really in the Peano way, it's really plane filling in, you know, like when you, so you know, at a given time, kt will be just you have filled everything in the inside, so gamma has visited everything inside a given domain, and this domain is growing because you continue sort of oscillating all over the place. So it's easy to see why that kappa equals 4, 8 are these critical values. Actually, we saw this in several computation, but again, to prove this statement is not as simple as that, but this is simpler than that. But okay, this is so these are the so-called phases of SLE. Okay, so there were, you know, until fairly recently, two very natural questions that were open questions for SLE. And and that have been solved. And the first one had to do with reversibility. So it was about, saying that if I take an SLE from A to B, in the upper half plane, or say from 0 to infinity in the upper half plane, or for A to B in the domain D, that if you were looking at the curve the other way around, that this had the law of an SLE from B to A. Okay, and of course, if you can't prove that this curve is the scaling limit of a lattice interface, then it's trivial, because in the discrete setting, the time reverse, looking at the interface in one direction or the other direction is the same. I mean, gives the same curve, but in the continuum, and if you don't know that it's a scaling limit of a lattice model where this reversibility holds, it's not clear how this works. And in particular, you see that, you have a real difficulty with the time parameterization already, because the way, just to illustrate that this is not something which is natural in the framework of SLE, the curve from here to here will be parameterized by the capacity seen from here. Right? So the natural time of this curve will be given by the size, by the way this guy grows with respect to the size seen from here. And in particular, most of the time, so I'm just telling you sort of general statement, most of the time, actually all the time, because will be spent at fairly exceptional points where the curve gamma is nicely exposed. The curve gamma will still be fractal, even on any scale, right? So if the curve gamma will still be fractal on any scale, for instance, when it is around here, the way the capacity seen from B will grow slowly. Whereas at some exceptional points, maybe the curve, will be like this, and then here the capacity seen from here will grow faster with respect, to some other, with respect to the amount of choke I use, or because I say faster and slower, but I didn't say with respect to what, but just in intuitive sense. So what is going to happen here is that basically the time parameterization will favor those parts of gamma, that are nicely exposed with respect to B here. But the time parameterization in the other direction here will be with respect to the capacity seen from here. And it's not very difficult to convince yourself that, in fact, the time parameterization in this direction and the time parameterization in the other direction are in fact singular with respect to each other, so that all the time in this direction is spent at points which the other one doesn't like and spends 0 time on. Right? So you have this, because you are exploring. The time is, you should think of this time as a strictly increasing function on the curve, natural time parameterization, but strictly increasing functions are not necessarily smooth. They can be the support of the measure of the derivative of the function could be supported on some weird part, and that's basically what happens. So roughly speaking, what I just want to say is that the time parameterization in one direction and time parameterization in the other direction, they have nothing to do with each other, and they have that much nothing to do that they are actually singular with respect to each other. Huh? Yes. And so to prove, in that framework, without any information about the fact that gamma, about any lattice model, to prove that the curve is reversible is something non-trivial. And it's even worse when kappa is larger than 4, because, when kappa is larger than 4, you are looking, what this process gives you is this increasing things like this, right? And the way the other guy is going to discover this mess, in the other direction, is just, you know, is maybe starting from exploring this and then a bit later exploring this. And so it's going to, yeah, maybe. So, you know, the way you're going to the Ks are going to grow is completely different from one another. So, because gamma was defined, you know, sort of implicitly once K was defined here out of GT, and because of the fact that the Ks, you know, are very sensitive, the way you fill in stuff is very sensitive to which direction you look at things, it makes life even more difficult. So this is a theorem that is, I think, about a little bit more than 1 year old, and that is due to Dapeng Zhang. So he's a former student of Makarov. Basically, he shows that kappa, so SLE for kappa equals for kappa smaller than 4 is reversible. So what I mean by that is that the law of the time reversal of SLE is still SLE from the other points. And as far as I know, okay, maybe I'm wrong, maybe I'm missing some reference. As far as I know, there is no full proof of the same statement when kappa is larger than 4. So it's clear that kappa larger than 4 has this additional difficulty here because of this fact that you have these Ks growing, so there is something even wilder going on. And so this, for instance, is a result, you know, that could be now still reached by pure, you know, SLE Loewner chain technology and proving certain things. So, you know, people understand better and better these stories. Now, there's another recent result, so that has been proven simultaneously and independently by Zhang and so maybe actually there's no G here. I think that's the correct Dapeng Zhang. Okay, I apologize for. Okay. And Dubeda. So I just want to emphasize, you know, that these people are not Lawler, Schramm, Werner, Smirnov, or Sheffield. You know that you have other people that, you know, proved what we couldn't prove. And this statement is about duality, what is called duality. And this means that if you take kappa larger than 4, so I just give a vague statement. So as I told you, kt, so I fixed t, then kt is something like this, and the curve, you know, this is just the hull of the curve that is inside. Okay? So roughly speaking, the duality was a conjecture formulated first by, formulated by the Duplantier and Kenyon, and okay, as soon as you start to playing with that, it's a fairly natural thing to say, is to say that if I look at this curve here, this is a curve which has many double points. Okay? But if I take its outer boundary, this is a random curve, which is a simple curve, because by definition, it's the outer boundary of something, so it's natural to believe that it's going to be a simple curve. And so if this guy is SLE kappa, in the inside, the statement is that basically the blue guy is, with quotation marks, some variation of 6 SLE 16 over kappa. So that it will still look like an SLE curve. And it will look like an SLE curve of some dimension. Because it's a simple curve, it will be something of size, smaller than 4. And this will be sort of the correct thing. So basically, to each value smaller than 4, or larger than 4 corresponds naturally a value of kappa which is smaller than 4 that is describing, roughly speaking, the shape of the outer boundary. So this is the duality conjecture, which is now proved. Of course, I haven't mentioned here that one thing here that maybe I should say here is that when kappa is smaller than 8, the dimension of gamma, so of the curve, right, not of kt, the dimension of the curve is almost surely 1 plus kappa over 8. so that you could compute directly things with that, and these were results. So the first full proof was by Fefara, building also on Rode Schramm, who had the lower bound, the upper bound and the upper bound, which is notoriously more difficult. But here now you have alternative proofs also by Loewner and of this fact. Of course, you know, as things go, you know, we understand things better and better, and then we start having simpler proofs of results that looked at first messy. So now there are approaches also by Scott Sheffield and Loewner of these things. Okay, so just to give you a general picture, so these two questions were basically, you know, 2-3 years ago, we would say these are the, you know, the clearly open questions, you know, for SLE that are important to understand and that may take some time to solve, but took less time than I expected because, you know, there are many clever people who start looking at these things and who can solve these things. So here now, you see in that picture, from my perspective, you know, in the SLE technology itself, the only missing part would be here, so that proves it's reversible. On the other side, that I guess it will take, okay, if it's doable, then one of these people will not spend much. I mean, will probably be able to do it if they haven't done it already. Maybe I missed the reference. So this is not to discourage you. It's just, you know, to show you that, roughly speaking, you know, most of the important natural questions that you can raise for the definition of SLE itself are sort of are solved. Of course, you can then, you know, start playing. There are plenty of, you know, questions you can raise about, you know, fine properties of the SLE path and showing that the SLE path has that type of points and not that type of points, doing decompositions of certain exceptional points, or looking at and all these questions are interesting. For instance, what Tom Alberts, who is sitting in the back of the room, has been looking at with Scott Sheffield, had to do with, you know, take an SLE kappa when kappa is larger than 4, you know, and look at the dimension of the intersection. You should correct me, Tom, if I'm saying something wrong. Computing the dimension of the intersection of the SLE path with the real line. And this is not just, you know, for fun, because it's also related to, you know, what people call boundary conformal field theory in their framework. So it's a natural thing to look at, and you hit, okay, maybe not as tough problems, but you hit these type of second moment estimates and correlations problems that were also around here. Okay, so that was just, you know, to give you a general flavor. And of course now it's nice because, you know, you can show everything and then says, okay, everything is fairly difficult, you know, if you look at these papers or that paper, take some effort, you know, to understand what is going on. Here the key basically to this, and actually then also to that, was to have some natural coupling between, basically, you start a little SLE here, right? And you show, roughly speaking, that by starting an SLE here, the law of the way it starts here is invariant, and what happens if you start an SLE on the other side, so that you can somehow commute, you know, that you can grow them from both sides directly, simultaneously, and couple them in some way, and then show that necessarily they will have to meet somewhere and be glued together, and therefore that you can shift back and forth the points where they will meet, and then therefore have this reversibility showing up. Okay. So this is just the SLE picture. Now, what I want to explain, so I also use this to recall certain general things about SLE, so that I can now describe some other questions and related objects. So both in what is called conformal field theory, and that we're not going to describe, but that now we start, you know, you saw maybe a glimpse of this by this complex valued observable f that we saw in the Ising model. And in general, what we are aiming at, what we would like to describe is not only one interface, right? It's everything. You know, we want to understand all the information that is contained in the domain. And so the natural way to encode the information about connectivity properties in the domain is what shows up. You know, the natural thing is not just one interface. It's more, and we saw that. Okay, it's a collection of loops. Okay, so we saw that in two. I mean, there are two examples. One example where we saw this would just be to take critical percolation, right, and look at the outer boundaries of all the clusters of both colors, right? So then one way, you know, what is a cluster? A cluster is basically some object, you know, that is living between a connected component of the complements of these loops, right? Because you have the outer boundary, and then you have the inner holes, right, which are outer boundaries of some clusters of the other color inside. So that is one example, right? So that if you want to describe everything, it's not just one interface, but it's more a collection of loops. And the other example we had was this FK representation of the Ising model, where again we had, you know, loops that were going around the clusters, and in fact there was really this notion, you know, with these loops consisting of things, you know, that had to turn at each time. And in some sense, you might say, well, that that the SLE picture was slightly artificial, because that was apparent in the Ising case, that we forced, in some sense, the fact that we wanted to have some special curve. So we used the boundary condition A, B, and like this, and which forced, you know, the existence of another special curve. Open curve, which was not a loop. And if you think about it in terms of the percolation, it's the same, right? If you look at percolation here, you have clusters. Of course, they may touch the boundary here, and so you have loops, you know, that go around the clusters, corresponding to the outer boundaries of the clusters. And the coloring, you know, of the two boundaries into two colors here, in order to create an interface here, was fairly arbitrary, right? The choice of the 2 points A and B was something which was not the most natural thing to do. So the natural question then is to say, well, okay, is there a way, you know, to describe this collection of loops? Is there a way to use what we've done so far, sort of understanding the interfaces, by this collection of loops? And so here, the answer is basically yes. And there are different ways to do it, but maybe I will start without referring to any, to do two approaches, and the name of Scott Sheffield is is the important one here. Basically trying to explain you two ways to construct these things without any reference to, again, lattice models. So imagine, well, maybe I will use reference to lattice models just to imagine that, you know, you have a loop where everything, you know, on the boundary has the same color. Okay. And in fact, this is basically what you hit, what you end up looking at in each of our discrete models, because in the discrete models, what we had in mind was, you know, coloring here everything in blue, everything in orange here, and exploring the interface between the two, right? Once you have finished exploring the interface, what you are left with, are domains. So for instance, this one, which is a domain where everything on the boundary is orange, and here this one where everything on the boundary is blue, and maybe this one where everything on the boundary is blue. Anyway, what you end up with are domains that you still have to explore where the boundary is given by just one color. So what is let me just, still use this color intuition to tell you what is the natural thing to do here. You still have blue and orange. Well, you just, you are here, and you start, you want to go into the inside and see what, you want to use still some algorithmic procedure. Okay. So the idea is that when you go to the inside, it's a mess. You don't see much. However, maybe, at some place, you believe that there will be blue loops floating around. Right? And because of self-similarity and so on, the blue loops will be more or less everywhere. As soon as you move a little bit, you will hit a blue loop. So that means that maybe, you start moving, and then you decide, okay, each time I see a blue loop, I have to go around it, like an interface. So roughly speaking, what you're going to do is basically you move here. Algorithmically, what you do is you move, and as long as you don't hit a blue loop, you're orange. Okay? But so you move here, and then you hit a blue loop, and you go around it, say, to the right. So here what you do is you hit the blue loop, and you start going around. Okay. So at that moment, what do you see? At that moment, now I have, when I've started going around the blue loop, I have a new domain, which is the slit domain here, where one big part of the boundary is orange, which is all this part here. And one little piece is blue here. But if this, if this blue guy, happens to be very large, maybe later on, maybe the blue part, because you have to go around a very large loop, the blue part, may get larger. So what this tells you is that if you start exploring a loop, right, SLE tells you how to finish to explore it. Because if you have explored this, then what you know is the way you have to continue anyway is via an SLE from here to here, because you have to go around the entire loop. Okay? So roughly speaking, what you are doing is, you start putting your foot in this mess, and then from time to time you will see little, blue starting things, little infinitesimal blue things. And starting from this infinitesimal blue thing, very small one, you just continue like an SLE in that new domain with the boundary condition given by the blue guy until you close the loop. So in general, when you start with a very small infinitesimal blue thing here and an orange thing here, in general, SLE will be very small, because SLE from here to here in that domain, these 2 points are very close, so it will just be something very small. But sometimes it will happen, exceptionally, exceptionally it will happen, that the loop will do something like that. And in the SLE picture, this will correspond, that if this are the two endpoints here, this would correspond, roughly speaking, to the fact that the SLE will have to get very close to the boundary because it has to go very far from these 2 points. So what I'm aiming at is roughly saying that the natural procedure that you get out of this, this procedure is that what you do by exploring in that way, right? So, okay, this is not a course on excursion theory, but roughly speaking, you are doing some excursion theory of SLEs. So remember, if you have a one-dimensional Brownian motion, yes, a one-dimensional Brownian motion in like this, can be decomposed into excursion. An excursion is a part of the Brownian motion, where the Brownian motion is strictly positive. At the beginning and at the end, it's 0. And on any finite time interval here, starting from 0, you immediately have infinitely many excursions. However, there's sort of a natural way to define excursion theory of Brownian motion that roughly says that I have an IID collection of these excursions and I plug them one after the other. Of course, this doesn't make sense because the number of excursions is infinite immediately, but still their length, most of them are very small, so that the total length of what you get by putting all these excursions one after the other will be finite and will be indeed your curve. So this is just this notion by just, and so here it's the same thing, that the process that you end up with by, exploring this mess here corresponds, the natural thing that you will end up will be just, putting one after the other SLE excursions. So this leads naturally to a variant of SLE, which is called SLE kappa minus 6, which roughly speaking is just nothing else than, plugging in one after the other excursions corresponding to discovering loops one after the other that are here. Of course, this is very hand-waving. Right? And so what Sheffield did in one nice paper was basically to say, well, I know how to, I can define this object, which is the sort of the natural thing you would get or guess from, exploring with these excursion theory that tells you that, that basically the loop, the law of a loop, because you say it's roughly speaking like an excursion of SLE, like and so these guys naturally define okay. And there's a natural thing you can do when you have a SLE, these things with these excursions, is then that as opposed to SLE itself, you don't have any prescribed target point. I just said you dip, you put your fingers in there, and then you close the loop, but I haven't said that I'm going here, there, or there. So in particular, it's important that once you close the loop, you have two options. Either you go to the outside or you go to the inside. Okay. So if you go, and in our, in the SLE framework already, things completely decouple, because seen from the inside, you see this domain, seen from the outside, you see the outer domain, and so you could basically just split these two procedures and have a tree-like structure. Each time you close a loop, you decide to go inside or you go to decide how to go outside. Yes?
Question. So once you look at compared to excursions, so once excursion Brownian motion is finished, you immediately departure for the next one.
Yes.
So what happens when you finish one loop?
So you don't. That's one point. You don't immediately departure for the next one. The thing is that if I have one guy, I finish here. There is no next one. Immediately I have, infinitely many small guys. There's no first one you start with next. Here it's the same. Basically, you finish the loop, and then you continue, and in some way, basically, there's nothing to explain to how to continue. You just, plug together after one another all these independent things and show that, in some sense, things are stable, or that the contribution of all these small ones, when you forget about them, that you don't make a big mistake.
Is there another sample there, like for the excursion program?
Yes. So it's just so if for those of you, okay, so this is a variant of SLE6. So for those of you who know Bessel processes, it's a very natural thing to do that. You have SLEs have to do with Bessel processes, and you have excursions of Bessel processes when they are of dimension smaller than 2, because they will hit 0, and then so it's just they are self-similar with a given. There's a natural exponent associated to each of these Bessel processes. That tell you basically what the local time here on the bound here is. That tells you something about the SLE process itself. So what Scott does in the paper is basically constructs this, what he called branching SLE kappa minus 6. So it's, roughly speaking, you define this thing, and you start exploring all the way. You have a sort of tree-like structure that starts from A. Okay. And now, once you have the tree-like structure, you can, so that's what he explains in his paper, is that when you have a tree-like structure, you have a definition of the loops, because the loops are, you can sort of, if you know all these branching things, you can recover what you want to call the loops in your tree-like structure. Okay. So there's actually an important thing that you should notice is that this definition works also when kappa is smaller than 4. Right? You don't need the SLE to have double points in order to make this construction. Sorry, this is variation of SLE kappa. To make this work. So this tells you, so what Scott's construction tells you, gives a constructive way, using SLE only, to construct a family of loops. And so natural thing is the conjecture is saying, well, this family of loops that you construct in this way is the scaling limit of the family of loops that you observe in the corresponding discrete model. As a matter of fact, sort of, I think Stas, he had in his proof of easing, it's 1, convergence of the discrete thing. 2 is going to be convergence of the exploration process. 3 will be convergence to the loop system, to the CLE story. And in fact, as a byproduct of Stas's proof, you would have that the family of loops that you construct in this way, by SLE kappa minus 6, the law of this family is actually independent of the point you start from. Because here there is still something you have chosen, which was the point A you started from. And it's not, I think, in most cases, maybe I should check with Scott, but I think in most cases it's an open question, no, it's not an open question because of what I tell you later, but at least from the construction here, it's not, or in that paper, it's not clear that the family of loops that you construct in this way, that the law of this guy does not depend on where you started from.
Does it have to do with
So that was what I was going to say. This is a nice construction, but there's one, in some sense, seen from this perspective, a trivial case. And this trivial case is actually was mentioned also in Stas's first paper, which is what you would do if you define in the percolation case. Actually, you note that in the percolation case, something special happens here, which is that kappa minus 6 is 0. So that the SLE kappa minus 6 I'm looking at is just SLE kappa. And so in the percolation case, things are, once you have convergence of the discrete exploration process to the continuous exploration process, you can play exactly that game. So you say, I start from A, and I explore. So imagine I have B, I have C, I have B1, B2, B3, B4, and so on. I start the exploration process here until, I have to decide whether to go here or here or here. This means I have created a loop here. So now you can, start one guy to the left and start one guy to the inside and continue and look at them independently. Because you have scaling, you have proved convergence of this guy to radial exploration and this guy to caudal exploration to the other B, it's quite clear and it follows pretty directly from the convergence to SLE results that I've told you before, that if you look at the law of the tree, of the discrete tree that you define in this way, that it will converge to the law of the continuous tree corresponding to these branching SLEs. So that's this full scaling limit of Kamiya and Newman, when basically saying that using branching SLE 6s, you can recover the entire loops, and so you can recover the entire collection of loops in the percolation case. It's a natural thing to state, right? I mean, it's a natural result, and it follows, so it's quite clear why they, in order to state it, they had to prove in some way the convergence of discrete exploration to SLE. Okay. So this is one way to construct some structure, right? And so this is maybe the first time where you see that using SLE, this time using SLE, you construct an entire two-dimensional structure where you see these loop systems. So of course, once you have closed the loop, you may also, start again here. In each of the loops, now you have still some monochromatic story. So you could start, again in each of the loops and construct, loops that are surrounded by other loops and so on to have this structure. So these loops that Scott constructs here are called sort of this collection of loops here that you get here constructing out of here. Okay, there are different equivalent ways to define it, but that's sort of what we call a CLE, Conformal Loop-ensemble. Right? Because it's a collection of loops, it has conformal invariance in it, and it has some special properties, but come back to that later. Now, again, if you look at Scott's paper, here there are, there are natural open questions, left here in Scott's paper. One would be just, prove directly using this guy that, using the statement that something, is invariant under the does not depend on the starting point, that you have some reverse, because we don't know that this is reversible already, it creates problems. Okay, I've skipped little details, about deciding in which direction to go around the loops and this type of things, but Now, there is another approach to these CLEs, which is sort of more maybe axiomatic and useful. So this is what we did together with Scott, and embarrassingly haven't finished writing up since several years now, so it's the type of thing, if you are a professor and have to advise your student or former students what to do and what not to do, this is exactly what you should not do, prove something and just be lazy or whatever and not write it up and let it, hang around for a long time, because that's sort of not only it's not good because as long as you haven't written everything up, you are never sure that things work out. But also it sort of sterilizes everything because everybody's waiting, to know what is actually proved in that paper and what you continue, or so this is the CLE axiomatic approach, which is say, okay, let's forget about SLE6, and let us forget about SLE, and let us try, to give, an analog of the exploration property of that led, in order to define SLE, one axiomatic way would be to say it's a random curve, it's conformally invariant, and it has this exploration property. So and then the curve, has to be an SLE. So this was sort of, let's try to do something similar to say, what do we have a random collection of loops. What are we asking for this what are the properties we ask for this random collection of loops? And maybe we can prove that then, there are only not that many possibilities. So the CLE axiomatic approach is basically the following: is you have a domain D, and you have a random collection of loops. And now I immediately say that one thing we don't know how to do, or that maybe Scott knows and I don't. I think Scott has ideas, but well, that's, okay, Tom knows Scott. So to say Scott has ideas is not a very useful statement, because he certainly has ideas. So you have loops here. So I was just saying that this works nicely, particularly nicely, if you are looking at collection of loops that are disjoint. So roughly speaking, this corresponds to this picture here when the kappa is smaller than 4. So in particular, it does not, it does not contain the case of the clusters of percolation or the easing loops that we looked at because they tend to touch each other. So, but it contains many models still. So suppose that you have a collection of loops gamma j, and it's quite natural, given already here this construction, to look just at the collection of loops which are the outermost loops. Like a cheesecake. Of course, we said that here in all our models, then later on we'll have loops inside loops and so on. Okay. However, if we have the law of this guy, we may then just decide that in each of the loops you sample a new, because of conformal invariance, you start again in each of the loops and you have this sort of successive definition of loops that you have here. Now, you have a random collection of loops, and this defines sort of this is a probability measure for each domain D. For each domain D, you have the law of a random collection of disjoint simple loops in that domain. Okay. So we ask two things. We ask one, so it's conformally invariant. So that means that if I take the conformal image of the random collection of loops I see in D, I define the random collection of loops in phi of D. Right? That's what you want, that the picture you see in one domain and in another domain are the same modulo conformal invariance. And of course, here already you see that this conformal invariance in some sense is stronger than the previous ones because the previous ones were conformal invariance with some prescribed point. Say, this starting point, that's the end point. So the group of conformal transformation with two fixed points is slightly smaller than this entire story. So you want this. And the second thing you want is the following property that is very natural if you think of coloring. So now I have D, so for any D and for any D prime subset of D, simply connected D prime. So I cut here, I have D prime, which is here. Okay. And I just draw this in blue, and I decide that my loops are red, say. Okay. So now what you do is that you cannot, you want to say that maybe you can compare the law of the loops in D prime that you observe in D prime with the law of the loops that you started with in D modulo some conformal invariance. You want to do some type of exploration property. So the natural thing if you think about the exploration property I've told you here, the natural thing to do was for any D prime here, we're going to define a new random domain, which is the domain that you obtain by taking D prime and cutting out all the pieces of the loops that go around, that go out of D prime. So this defines, for each sample, so you sample gamma j is a sample of PD. You do the sampling, and then you have a random subset of D prime. And then what you're asking for this, what you want is that the law of the red loops that stay in the remaining domain, so the law of what happens here, given the rest, conditionally on this, the law of these red loops is just the law you started with in this new domain, in this sort of D tilde. This is D tilde. Okay. So if you think in terms of coloring, this is really something natural because you have this domain here, and imagine that everything is blue here on the boundary, right? And that the loops that you're looking at are the outer boundaries of the red clusters. So this means that everything in between these red clusters is blue. So, and in particular, because these are the outer boundaries of the red clusters, the outer boundaries have blue neighbors. So when I cut something out here, this boundary here is blue. So you're still in the monochromatically blue boundary once you go around this. And so you just use this intuition to say, well, that anyway, if these are nearest neighbor interfaces, these guys, it should have, and this is the scaling limit of these guys, it should have this property. And you see that here this exploration property is slightly, looks slightly weaker than the conformal exploration property of the SLE curve, because the SLE curves were saying it for any time, I know I'm okay. Here, we don't have a one-dimensional time to start with, but we just say that for any d prime, if I condition on this and cut this out, I'm still in the same picture as the one I started with. So if you have these two things, we call, these laws, P of D, the law of a simple CLE. Okay, so now there's one thing you can check sort of fairly directly, just by giving you some ideological things. And everything I'm saying here, is as a portion of a big paper, so I don't want to I'm sort of going, during sightseeing, of big, long papers. So what you can roughly say, and intuitively it's quite clear, is that if I have a CLE, if I have this picture, you could try to explore it in that way. Right? Suppose I have a CLE, and then what happens, to my CLE when I try to explore it in this way by just, putting your fingers here, and each time you hit a loop, you go around it. What one can prove is that necessarily, right, if you have a CLE and you start exploring it in that way, you will be, and you have started exploring a loop of a CLE here, then necessarily the way you're going to finish because of conformal invariance is actually satisfies the conformal the exploration property. And therefore, what you can prove is that necessarily a CLE that satisfies this can be explored by an SLE kappa minus 6 process. And so therefore, this tells you that if I have a CLE guy, right, then it corresponds exactly to the loops defined by SLE kappa minus 6 process. And therefore, if CLEs exist at all, right, the set of loops that is defined in this way does not depend on the choice of the initial starting point. I don't know if this is very clear. I'm just saying, suppose I have a CLE. Right? Explore the CLE, prove that then, it necessarily has to be explored, like SLE kappa minus 6 for some kappa. And so therefore that the law of the loops of the CLE are exactly the law of the loops that are defined by a SLE kappa minus 6 branching story when I start from any point. Right? But because the law of the CLE does not depend does not have any specified point, I could have started from anywhere and I would discover the same CLE. So if these guys exist over there, then this does not depend on the starting point. Okay. So there's one thing, one has to be, this axiomatic approach, it's, from my perspective, still a slightly, okay, well, we have to check. You have to check with Scott before working on that. For me, at least, it's something I don't understand how to make it work when kappa is, for the SLEs that touch each other. Probably, the definition is just still more or less works when they are touching each other, but then you have to Okay, maybe this still works, but anyway, what I'm going to say now doesn't. Okay, I have to be careful with the machines and the recording stories. So I can continue, okay. So the next, yes. How do I guarantee that I catch all the loops? Well, I mean, that's part of the things you have to check. And of course, that you have to use certain things that I haven't said about the fact that you always go to the inside of the domain in some way. So that you don't add, I mean, okay, it's a good question. That's all I can say. Yes?
A very naive question. That picture, I don't know if I made the right picture. Even if they don't touch, they can accumulate.
Yes, they do accumulate.
What they give has empty interior.
Yes, right. So that's one paper by Sheffield, Wilson, and Schramm, I think, where basically they compute the dimension, Hausdorff dimension of the interior of what is left, you know, outside of the loops by an SLE kappa kappa minus 6. So you can compute the dimension of fractal dimension of this guy by SLE means. Kappa minus 6. So it's, how can I say that? Let me put it this way. So the Brownian example is not very good, but you know, how can I say? You should just think, okay, that's another way to define. You could actually forget about SLE kappa kappa minus 6 and just say these are just, you know, excursions of SLE kappa, you know, put one after the other. The problem is that when you do this excursion one after the other, at some point you need to, you know, it's useful to have another point. You know, at least to know what the time you're using is and how to define these things. And when you are defining these things with this other prescribed point, then naturally you have sort of a drift induced there. So these are the SLE kappa row processes that we defined with Greg and Odette because they are the natural things to do when you have these stories. But you should just think of SLE excursions, you know, put one after the other. The SLE kappa kappa minus 6 has the property that basically the excursions of this guy is just an SLE aiming at the target point. The difference here, you know, is that somehow it's not just simply an excursion because it's an excursion that is aiming towards this special point, which is the begin where you started doing this. So, and this point is also moving. So it's a natural thing to fix another point and to see where this point is with respect to when the SLE is moving. What did I want to say now? Yes, so another approach to CLEs so I don't want to spend too much time with that because I want to say things about all the other things because there are plenty of them. Another approach to CLEs goes as follows, and maybe how can I explain this? So these are the so-called Brownian loop soups. And the way we hit these objects, which are actually quite natural. Initially, you know, the first time we tumbled on this with Greg and Oded was by trying to understand, you know, things having to do with uniform spanning tree and Wilson's algorithm. And so I think Vincent will give a short presentation maybe tomorrow or, of Wilson's algorithm and the way to simulate uniform spanning tree and why they are related to these FK models that we're looking at. Basically, you know, when you are looking at the loop erased random walks, you are erasing loops. And if you look at the loops that you have erased, and you keep track of them, then it's a very natural object to define the things I'm going to define now. So a Brownian loop soup is the following. And in a way, let me just try to motivate it from the picture we have there. Suppose I have one CLE. Let's say this is the green CLE. Okay. Suppose I have a CLE here that defines loops here. And suppose I have another CLE, independent one, in the same domain. Say this is the blue one. And look at the union of these two things. Then, of course, you have two options. Either actually the union, you know, clusterizes into everything, you know, because we said the loops are everywhere, so maybe they immediately create infinite chains of loops that go all over the place, and then the game is finished. But maybe you're lucky, and maybe this picture actually still has clusters. So maybe now you have new loops that are given by the union of the previous ones. You know, you look at clusters of loops like this. And it's a sort of trivial exercise to check that if the law of the blue loop, the blue CLE and the law of the green CLE satisfies the fact that when you take the union of two guys, you still have loops, then the orange guy is still a CLE. It's simple. It's not trivial, but a simple exercise. So this indicates that in some sense, you know, the family of CLEs, they have some sort of additive structure, right? So that you can take one, you can take another one, and you put them together, and you get a third one. And so maybe one given, you know, one CLE itself, maybe it's infinitely divisible and, you know, has been created by, you know, adding many very thin CLEs. So you may ask, okay, what is the sort of infinitesimal, you know, if you believe that a CLE, you know, is just obtained by, you know, adding, you know, many very, very, very thin other CLEs that are independent in that way, you ask the question, okay, what is the infinitesimal, you know, CLE with infinitesimal intensity? And then you end up with this construction. And again, it's a story about infinite measures, so maybe I should spend a couple of minutes with that. So the first thing is that there exists a natural measure that we call the Brownian loop measure with Greg, which is a measure mu on Brownian loops. So this measure mu on Brownian loops is a measure on basically loops in the plane. And we do not specify the starting point nor any time parameterization. It's just a measure, you know, on loops in the plane. And this is a measure on Brownian loops, and the way you should think about it is just, you know, the limit. So this is the scaling limit of the measure on loops in, say, delta z squared that assigns mass 4 to the minus n of L to each loop L, where n of L, its number of steps. You know, you have a natural way, you know, you just say for each possible loops that closes up, you put a mass that is just, you know, the probability that starting from somewhere I follow exactly that loops and closing. and you take the scaling limit where delta goes to 0, clearly this will be, okay, just so happens that, you know, everything, nice things cancel out so that this will converge to a finite measure. And this measure will be supported, you know, on Brownian loops, two-dimensional Brownian loops. Now, this measure has a very nice property, which is that it is conformally invariant without any scaling factor. So this measure satisfies the fact that if I get mu d is mu restricted to the loops that stay in D, then phi of mu d is just mu of phi of D. So in some sense, this measure on Brownian loops, you know, is because of conformal invariance of two-dimensional Brownian motion, it will inherit a property of conformal invariance, and actually it will be exactly this one. So, you know. So, of course, one important thing about this measure on loops is the following, is that, so that means that I take any small domain, or any large domain, or any three different domains. If I look at just, you know, the mass of the set of loops that stay here, here, or here, they are just conformally equivalent with respect to each other. So in particular, the total mass of the set of loops that stay here, here, or here with respect to mu is the same. So clearly, this mass has to be infinite, right? Because if I look at the mass of guys that stays here, it's the same as the mass of loops that stay in the smaller domain. So they are equal, but one is larger than the other, and so they must be infinite. Another way to say is that by definition, this measure mu is scaling invariant, so you have an infinite mass on very small loops. But the important thing is that the mu mass of the set of loops, say of diameter 1, that stay in a unit disk or something like that, this one is finite. Okay. Now you do the same procedure as the Brownian, as in the Brownian excursion case. You just, you know, sample, so what we call a Poisson point process with intensity mu. You just, so I cannot give you a course on that. The usual way I describe it is to say just you have a measure mu that that describes in some way the fact that some loops are more have more likely than others, but it's an infinite measure. And now you just, you know, sample according to this loop picture. So in other words, you let it rain if you want. You let it rain a certain time. You let it rain Brownian loops, and of course all the Brownian loops that fall, they are independent of each other. You know, they fall down independently, and you let it rain a certain time c. Right. So in our thing, you take a Poisson point process with intensity c times mu d if you are. So this is exactly the same story as in the Brownian excursion story, if you want, in some way. You know, in the Brownian excursion story, you know, you are going to let it rain Brownian excursions during some time c, right? So then the picture is, you know, at certain times here, what falls down is, you know, excursion. So this is the time, but it's not the Brownian time. But you let it run. What is going to fall down, you know, at each of this artificial time are, you know, so excursions. And because of the fact of the mass of the small Brownian excursion is infinite, basically on each small time interval, anyway, you will have infinitely many very small excursions that did fall down. However, what will happen is that if you look at the total length of all the excursions that did fall down here, what you get here is finite, so that you can, you know, plug in one after the other all these excursions that have fallen down in the sort of lexicographic order from left to right, and you reconstruct the Brownian motion. Here it's a little bit the same, except that what is falling down, you know, the pictures that are falling down are not just one one-dimensional loops, but there are two-dimensional loops somewhere there, and then you're not putting them one after the other in lexicographic order, just looking at the picture that you observe here by taking the union of all the guys. And as here, you know, the total length of what you get here is still finite. Here, in the same way, you know, things do not explode. So what you can prove, and which is not very difficult, is that when C is small, the union of these loops will create clusters. So if you don't let it rain long enough, the loops will clusterize into clusters that are disjoint. So when you have disjoint clusters like this, okay, you may ask, what are the properties of these clusters? Outer boundary of the connected component of this union of all these loops. And it's not very difficult to prove two things. That when C is small, you have islands. So you have these, and when C is too large, they clusterize into one single connected component, almost surely. So that's one thing. The other thing is at the critical value of C, it's also possible to prove by soft arguments that do not use the shape of the loops, say, that if you are at the critical value, you still not clusterize. You still have loops. And you can prove things, and this is part of the things we have to write up with Scott, is that in some way, if you are strictly below the critical value, loops, you have some estimates that tell you that the loops are not too close to each other, because you still want to have the property that by letting it rain a little bit, it will not clusterize. Okay. Now, there's a statement which is actually not very difficult, which is that if I am in this configuration where I let it rain these Brownian loops, and I take the hulls of these things when C is small, that these orange guys satisfy the CLE. They satisfy the CLE axioms. So you just use basically the fact that, well, if I look at the CLEs here, so I cut out this guy here, right? So the first thing you do is, well, anyway, you have to erase all the Brownian loops, that went out of this domain. You have to kill them because and then you have to kill the Brownian loops that touched these Brownian loops that you have erased, and so on. Right? And then by our procedure, this means that, because the loops are finite, you will end up, this procedure will end at some point in the infinity, when you do this at infinity, and you will end up exploring all these things. Okay. But then you use the Poisson point process representation, the fact that the measure mu satisfies conformal invariance, to say that conditionally on this, the fact that you have explored this is independent, actually, of what happened to the loops, that did not touch this. So here you have a plain CLE, and you have conformal invariance here. It just comes because of the conformal invariance of the measure mu. So this is easy to prove that when C is small, you get this construct a CLE. Okay. So if you know that you construct a CLE here, actually you construct many CLEs, because if I said that there was a critical C0, such that for any C smaller than C0, you construct a CLE. So we have a one-dimensional family of CLEs here that is constructed here. Now there are several arguments that have to come into play. The first argument that you want to, the goal basically is to prove that this will construct all the CLEs for kappa smaller than 4. Because remember, a CLE corresponds to an SLE kappa minus 6 for some kappa. So we want to prove that this will construct all of them for kappa smaller than 4, and therefore show that all the SLE kappa minus 6 construction for kappa smaller than 4 are independent of the starting point and give these construct the same object. right? So you see here, out of nothing, we just said, let it rain these Brownian loops, right? So the important thing is we used just one ingredient was that this Brownian loop measure was conformal invariant. So by letting it rain these Brownian loops, we construct some two-dimensional conformal invariant structure. And in that two-dimensional conformal invariant structure, we can recognize interfaces and loops. Yes? No. It's really sort of okay. If you want to define it, I mean there are other ways to define it, but one way would be to say if you want to not to view it as a limit of a Brownian of a self-avoiding. So okay, you could say okay. Let's define first the Brownian loop started from 0 and having length t, time length t. So this is something easy. It's just what you call a Brownian bridge. So the real part and the imaginary part are just Brownian motion conditioned to be back at the origin after time t. If you know, for instance, the Fourier transform, I mean the Fourier coefficients of a Brownian, that the Fourier coefficient of a Brownian motion on the finite time interval are just, IID Gaussians. This just means you condition the first value of the Gaussian to be 0, the one that gives the linear terms, and the other ones are IID Gaussian, so it's just or you just say that, it's a Brownian motion minus t times the end value of the Brownian motion. Anyway, so this defines a measure on loops that are rooted at 0 and have, time length t. Then the trick is to say, okay, we want t to vary, right? So we take some measure on t. So this would be, say, dt over t squared, for instance, or something like that. And then we want the starting point to vary. So we do some d squared of z, would be basically we integrate over all port signal starting points. And then you have to do something which is now erase the information where the starting point actually is. And so that in some sense the dt over t squared becomes a dt over t, because in a loop of length t, you roughly have t times more possible starting points than on a loop of length 1. And so this guy becomes scale invariant. So there are different equivalent ways to define it, and this is what we did also in the paper with Greg on the Brownian loops. Okay, there are many other ways to do. I mean, if you look at the paper of mine on self-avoiding loops, you see that you could also just do the same by, instead of letting it rain Brownian loops, you let it rain percolation clusters. But it's the same shape. So, but it's better to look in terms of Brownian loops because of what I'm going to say after the break. So, so what one can prove then, so roughly speaking, is that for any c smaller or equal to c0, you construct a CLE, and therefore you construct something that has been constructed by an SLE kappa minus 6. Now, it is easy to identify the relation between C and kappa. The reason is because of this exploration type of this that you have here, which is that when I start exploring, say, here, and I want to compare what it means to explore here in the domain D prime and the domain D. What happens is that if I start exploring here in the domain D prime, I explore this. Now, if I start exploring the domain D, I have to add to the picture the loops that went out of D prime. Right? So the exploration here will not change unless I find a loop, that hits this cluster. Otherwise, the cluster is not touched. And so this observation, what we call restriction type defect of SLEs, tells you basically how much this exploration guy has a restriction defect depending on C, because the intensity of these loops here depends on C. And so this allows to identify which kappa corresponds to which C. And so what you see here is actually that, so you have an explicit formula for kappa in terms of C, or for C in terms of kappa. And you recognize then, you're happy because you recognize that this time you let it rain here is what the physicists call central charge. Okay, this is some well-defined object in physics, in conformal field theory, and the central charge has to do with the central charge of certain representations of some infinite dimensional Lie algebra. I mean, the central charge of certain infinite dimensional Lie algebras that you classify the representations and where the exponents came out first by looking at certain representation of certain infinite dimensional Lie algebras. That's how physicists did, and they produced these numbers. Okay, anyway, so here you have this quantity C, but here it's quite clear what C means. So what you get here, and the other remark that you can make is that once you have the relation between C and kappa, on kappa and C, which holds for any small value of C, this is something that you know, because when C is small, you can prove that these will create loops. Then what will happen is that when kappa, if kappa, for any kappa smaller strictly than 4, the CLE that you get here basically will never get close to the bound. I mean, the loops, big loops, will never get very close to the boundary because they are like SLE kappa curves, which tend to be quite far away from the boundary. And as Scott, I mean, as Tom knows, they are repelled by power law time repellence from the boundary in some way. And this, you can prove that when kappa is smaller than 4, this implies that you are not at the critical value. Because that means that if you are kappa strictly than 4, the loops, they are repelled. The probability that they are very close decays somehow in a power law fashion, and therefore you can still, there is still room for adding little things without them clusterizing. So this tells you that for any kappa smaller than 4, you cannot be at the critical value at which this thing clusterizes. And you have seen that C of kappa or kappa of C is an increasing function of C that increases continuously and starts from 0 and goes all the way to, starting from 0. So out of this, you get that the only kappa correspond to the critical value can be 4, and therefore that you get all the SL, that for all the times that are smaller, all C is smaller, you get the entire span of SLE kappa, kappa minus, from the CLE of parameter kappa for any kappa smaller than 4. So what I say is just by looking, at this constructive way to construct CLEs by the Brownian loop soups, the conclusion you reach is that you construct all CLEs corresponding to kappa smaller than 4, or kappa smaller or equal to 4, and therefore you construct all simple CLEs because a simple CLE anyway had to correspond to an SLE kappa, kappa minus 6 for some kappa smaller than 4. So the conclusion is that the following: the guys you construct in that way are the only simple CLEs. There are no other ones. And they are the same than the CLEs you construct by SLE kappa, kappa minus 6 for kappa smaller than 4, or smaller or equal to 4. So therefore, so byproduct of this is that the guys, the loops you created by SLE, by these branching SLEs for kappa smaller or equal to 4 are indeed CLEs with that axiomatic approach. Okay. So that's an example, basically, of a model where, without direct reference to any discrete model, you just try to cook up to find, what are the continuous models that we could possibly define that have conformal invariance in them. Is there a way in these models to construct, to view interfaces or to construct loops? Well, but then, then we're immediately stuck like we were for SLE, in the sense that basically they're all the same. You only have a one-parameter family of these loop systems, and sort of an SLE in some way is in correspondence, a one-to-one corresponding with actually an entire loop system. So indeed, the SLE, gives the information. Once you have the information about SLE, you have the information about an entire loop family. Okay, I will make a break now. until past, and then I will try to speak about another two-dimensional structure, which is called the Gaussian free field, and try to explain very briefly basically why this one is also related to this story, how it is related directly to the loop soup, so basically I will maybe not do quantum gravity because that would be too long. Just sort of explain, so speak about work of, again, Sheffield, Schramm, Dubeda, the same one as we had before, and Lejean.